Okay, everybody, let's go back to relative humidity. So actually, let's finish up with dew point first. So here are the dew point values that you should have been able to get by using the reference table. So here we have 19 degrees, 5, 10, another 10, -7, 3, and 17. Now again, these are not measurements of air temperature, they're measurements of humidity. And the closer the dew point temperature is to the air temperature, the more humid the air is. And the further away the dew point temperature is from the air temperature, the drier the air is. And, well, I'm jumping ahead a little bit, but there's even a pattern here, too. Here we can see a dew point of 19 and a dry bulb temperature of 22. Those numbers are pretty close together. So to me, this would indicate relatively humid air. Now here we have that dew point of -7 and a dry bulb of 9. Those are pretty far apart. So this would be dry air. And this goes back to one of the relationships that we were saying in the other video. When the air temperature is high, the air has a greater capacity to hold moisture, and we can see that reflected in the dew point. When we have a higher air temperature, we have more water vapor, if it's available. It wouldn't be available in a desert, but in general, when the air temperature is warmer, we typically have more humidity in the air. The air can just hold more water. Over here, we've got a cooler air temperature, and we can see a lower dew point. This is drier air. Cooler air can hold less water. So let's shift over to relative humidity now. Relative humidity is just a different way of measuring moisture. So there's two ways that we can assess the amount of water vapor in the air. One is dew point, the other relative humidity. Now, relative humidity is kind of a different thing than the dew point temperature. With relative humidity, we're basically comparing the amount of water vapor in the air to the capacity of the air to hold water. Now, I remember when I was first learning about this, I found this definition a little confusing. And I think, for me anyway, what really helped clarify it was remembering that when we compare something, well, we can compare it in many different ways, but a mathematical way of showing a comparison would be with a ratio. And this ratio really made relative humidity quite a bit easier for me to understand, and I hope it does for you too. If this definition makes sense to you, then you're good to go. But I think for many people, this will be helpful. So I'll write RH for relative humidity equals the actual water in the air, actual H2O vapor, divided by the capacity of the air to hold water. And it's shown as a percentage. So relative humidity, you hear 80% relative humidity, 100% relative humidity. And that's really what we're doing. We're dividing the actual amount of water vapor in the air by the capacity of the air to hold that water. Now remember, capacity of air is dependent on temperature. So the higher the temperature, the greater that capacity becomes. So temperature will affect your relative humidity values. And that's something that we'll take a look at. So let's flip the page over. And now we're on page 19. Now, one of the problems with relative humidity, and I honestly think relative humidity is really a kind of terrible measurement of water vapor. I think dew point is far better Relative humidity, though, is a percentage, and people like percents. They're easy to understand. You know, on the news, the weather person, the meteorologist, will say relative humidity 80%, because people understand that. You know, people like percentages. But there's some flaws with relative humidity that dew point doesn't have. And if we take a look at this, let me, up at the top, okay, write our little formula again. So we'll say relative humidity is equal to the actual amount of water, actual H2O, divided by the capacity. Well, this is essentially a fraction. And the denominator of this fraction is dependent on temperature, which means that our relative humidity could be changed by a changing amount of water, but it could also be changed by a changing temperature. And temperature in itself is not a measurement of water, but it will affect the relative humidity. And this is something that often happens. So if we have, say, really cold air, a really, really low temperature, if we have a small number in the denominator, a really low temperature, that's going to have a big impact on our relative humidity, and vice versa. So if we take a look at this relationship in more detail, if we start out with an increasing temperature, temperatures increasing throughout the day, so I'll label this temperature, the capacity is also increasing. So if we pretend that these like little containers are air, the capacity is increasing as the temperature rises. This is a pattern that we see daily. In the morning, the temperature is cooler, and then as we approach noon and maybe even like 2, 3 in the afternoon, temperatures are usually at their highest, and we are at our greatest capacity. So maybe this is like afternoon, and maybe this is like early morning. Maybe even really early morning, maybe like 5 o'clock a.m., something like that, really, really early. So in the early morning, before the sun rises, we have a low capacity to hold air. And as the day goes on, and as we move into the afternoon, into our warmer temperatures, capacity is increasing. Now, if we go back to our fraction for a minute, in this example now, if we increase temperature throughout the day, capacity is increasing. Now we're increasing the denominator of a fraction, so this means that we're going to have a decrease in relative humidity. As the value of the denominator increases, we deal with a smaller whole, like 1/64 is a lot less than 1/2. We have 64 in the denominator instead of 2. So the larger the denominator, the lower our relative humidity. So as the capacity increases, our relative humidity actually decreases. And to me, this is kind of a flaw, or just something that's not very good about using relative humidity for the measurements, because it's impacted by temperature changes. So if we assume that the water content stayed constant the entire time, the water vapor didn't change. And I know I'm saying water a lot, but when I say water, I'm really talking about water vapor in this case. But the water vapor stays constant. We still have a changing relative humidity because the capacity of the air was changing. So in this example, we had a decrease in relative humidity, even though the water vapor content didn't change at all. And that's one of the problems with relative humidity. A dew point measurement is not affected by temperature. A dew point measurement is a true measure of water or water vapor. It's not going to be influenced by temperature. It's going to it's going to, you know, give you a precise amount of water. So sometimes students will ask me, well, why do we even use relative humidity at all if it's got this issue of being flawed with temperature changes. But I think it just goes back to the fact that relative humidity is measured in percentages. People like percentages. Somebody on the nightly news is probably not going to be talking about dew point because that's not going to mean anything to most people. And one of the jobs of the meteorologist is not only to make measurements, but to communicate the weather effectively to a large audience. And percentages really lend themselves to that. Dew point doesn't as much. But this is one of the issues with dew point. We can also see the reverse of this situation too. If we have a really cold temperature, we're going to be having a low capacity, and that could give an artificially high relative humidity. So we could see on a really cold winter day, when the air is very dry, a deceivingly high relative humidity, just because the capacity of the air is so low that the relative humidity is high. So that's the basic idea. So in this case, if temperature increases, and moisture is constant, then relative humidity is going to go down. Now, for this reason, we see relative humidity change throughout the day. And on a normal day, we have our coldest temperatures in the early morning, then, as you know, it gets warmer, and then in the evening it starts to cool down again. We have our highest relative humidity when the air is at its lowest capacity to hold water vapor, which is the coolest time of day, which is typically at about 5 o'clock a.m. Sometimes students say midnight, but 5 o'clock a.m. Or around there, right before the sun rises. Throughout the course of the night, the earth has been cooling off all night. So right before the sun rises is when we're going to have our coolest temperatures. And since we have our coolest temperatures, low capacity, high relative humidity. We see our lowest relative humidities when it's warmest. So here we would have our lowest relative humidities at the warmest time of day. Maybe around 3 o'clock p.m. or so. Now, if we just slide this up here, if we look at absolute humidity, now we're actually looking at water vapor content. So now in this example, we have a relative humidity change. Same concept. These are like, containers representing the air. We've got our relative humidity is now increasing because now the water content is truly increasing. And we actually have an increase in the water. So now our water vapor increases. And so does the relative humidity. So one of the things that's confusing about relative humidity is it can change because the water vapor is changing, which makes sense. But it can also change because of temperature and the air's capacity to hold water vapor changing due to a change in temperature. That's a strange thing about relative humidity. And I've mentioned this already. I really don't like relative humidity as a measurement. It's kind of got this bias, or it's influenced by temperature. Most of the time it's not a huge problem though. But it is a little bit of an issue at times. And that's why I prefer looking at the dew point temperature to assess water vapor in the air. Okay, what I'd like to do is same as before, but this time I'd like you to use that chart in the reference table to fill in your relative humidity values here. And in the next video, I'll put the answers in there. And yeah, if you could just go ahead and fill those in. And the next video is going to be shorter, only a few minutes. And then we'll talk about what I'd like you to do from there. Okay, good luck.